Welcome to the 9th lecture on the category of vector spaces titled Dimension. First, let's review our previous lectures. As a convention, all vector spaces in this lecture are over a fixed scalar field K. A vector space V is finite dimensional if it is a span of a finite subset, that is, if it is finitely generated. Finite dimensional vector spaces have bases, that is, spanning linearly independent subsets. A subset B of a vector space is a basis of that vector space if and only if it is a maximal linearly independent subset for the inclusion. This lecture introduces the notion of dimension and proves various important results about it. Dimension is a full invariant of finite dimensional vector space, and it's simply a natural number. It is the most important notion in finite dimensional theory, and therefore we will spend quite some time trying to make sure we understand it properly. The theory of dimension rests on the following fundamental result. Let V be a finite dimensional vector space. Let L and S be two finite subsets of V, such that L is linearly independent and V is a linear span of S. Then the cardinality of L is less or equal than the cardinality of S. The proof of this result follows a technique akin to Gauss elimination. But first note that the result is obvious if S is the empty set, since the singleton 0 is a linear span of the empty set, and the only linearly independent subset of the singleton 0 is the empty set, whose cardinality is 0. Also note that if S is a subset of our vector space, and L is a linearly independent subset of the linear span of S, whose cardinality is strictly greater than the cardinality of S, then there exists a subset L' of L, such that the cardinality of L' is the cardinality of S plus 1, and of course L' is still linearly independent. We are going to prove our result by induction. First, note that if L consists of two vectors v1 and v2 and is linearly independent, and if S is a singleton, W, and L is a subset of the linear span of S, then first, since the span of S consists of the multiple of W, we have that v1 must be lambda 1 times W and v2 must be lambda 2 times W for lambda 1 and lambda 2, two scalars. But note that since L is linearly independent, neither v1 nor v2 can be 0, therefore neither lambda 1 nor lambda 2 can be 0. But on the other hand, the linear combination lambda 2 v1 minus lambda 1 v2, which is lambda 2 lambda 1 w minus lambda 1 lambda 2 w, that's 0. So we found a linear combination of the vectors in L which equals 0, yet the coefficients, which are lambda 2 and minus lambda 1 here, are non-zero. This contradicts the fact that L is linearly independent, and therefore we must conclude that if F is linearly independent and in the span of a single vector, then its cardinality is no more than 1. Now assume that for some non-zero natural number n, if L is a linearly independent subset of the linear span of S, where S is some set of cardinality n minus 1, then the cardinality of L must be less or equal than the cardinality of S. Let now L be a set of n plus 1 vectors, v1 to vn plus 1, and let's assume L is again linearly independent. And let's assume also that L is a subset of the linear span of some S, where S has n elements, and I write S as W1, etc., Wn. Now, since the linear span of S consists of all the linear combinations of vectors in S, we must have that for any j between 1 and n plus 1, V sub j is a linear combination of vector W1 to Wn. I write it as V sub j equals the sum for k equals 1 to n of alpha sub k superscript j times Wk, where the alphas are all scalars. In my notation, alpha superscript j subscript k means that it is a coefficient for Wk in the linear combination expressing V sub j. Now assume in particular that for all j between 1 and n plus 1, alpha superscript j subscript 1 is 0. So what that means is that in all the linear combinations I have written here, the coefficient of w1 is always 0. Then it means that v1, v2, etc., vn in particular is a subset of the linear span of w2, w3, etc., wn. But then v1, etc., vn is linearly independent as a subset of L. It has cardinality n. Yet it is a subset of the linear span of a set of cardinality n minus 1, namely w2, etc., wn. And I assume that cannot happen by my induction hypothesis. So it's not possible that alpha superscript j subscript 1 is 0 for all j's. So we may assume with that loss of generalities that alpha 1, 1 is not 0, and as a scalar in a field, it has an inverse. So now I'm going to do my quote-unquote Gauss elimination. And I'm going to calculate for each j between 2 and n plus 1 a new vector v prime j as v sub j minus alpha superscript j subscript 1 divided by alpha 1, 1 times v1. And the whole point is to observe that v prime j is in the linear span of the set w2, etc., wn. Because we exactly calculated v prime j so that the w1 component in the linear combination of v sub j is eliminated, is cancelled. Moreover, notice that if you take a linear combination of the v prime vectors, which is equal to 0, then up to replacing v prime j by its expression in terms of v sub j and v1, then you see that we obtain a linear combination of the vectors v sub j, and they are linearly independent, so we can conclude that the coefficients of our linear combination of the v primes must all have been 0. So the collection v prime j for j between 2 and n plus 1 is linearly independent. So let's see what we have. We have the set v prime 2, etc., v prime n plus 1, which is a set of n vectors, and it is linearly independent. And it is also a subset of the linear span of the set w2 to wn, and that's a set of n minus 1 vectors. But our induction hypothesis tells us that this is impossible. Therefore, our theorem is proven. It is impossible to find a linearly independent family of n plus 1 vectors inside the linear span of n vectors. And so, as we have discussed, this concludes our theorem. So we now introduce a fundamental notion of the dimension of a finite dimensional vector space. So let's start with a corollary of our main result. If V is a finite dimensional vector space, and if B and C are both bases for V, then the cardinality of B equals to the cardinality of C. In other words, all bases of a finite dimensional vector space have the same cardinality. Since B is a linearly independent set, it's a basis, and C is spanning the whole vector space, it's a basis. We must have as a previous result that the cardinality of B is less or equal than the cardinality of C. But this is symmetric. C is also linearly independent as a basis, and B is also spanning as a basis. So again, you must have that the cardinality of C is less or equal than the cardinality of B. And so we have shown indeed that the cardinality of B and C are equal. Thus, if V is a finite dimensional vector space, then the common cardinality of all the bases of V is called the dimension of V. So the idea of a dimension is we basically count how many elements must a basis have, and it doesn't matter which basis you use to do that because all the bases have the same number of elements. So that actually immediately gives us a new way to prove that in a finite dimensional space, a given subset is a basis. So if B is some linearly independent subset of a vector space of finite dimension, and if the cardinality of B is the dimension of your space, then actually B must be a basis. Similarly, if B is spanning your vector space, and the cardinality of B is the dimension of the vector space, then B is a basis of your vector space. This is very important. So now you only need to check, for instance, linear independence and count how many elements you have in your linearly independent set. if you already know the dimension of your vector space, you can conclude whether you have your linearly independent set is a basis or not. So let's prove this. And for instance, to prove bullet point 1, I'm going to prove that if B is a linearly independent subset of my vector space whose cardinality equals the dimension of my vector space, then B is maximal linearly independent and therefore a basis. To do that, first let's exhibit some basis of our vector space. Since our vector space is finite dimensional, such a basis exists. Let's call it C. Note that the cardinality of C by definition is a dimension of a vector space. Now, since I want to prove that my B here is maximal among linearly independent subset of the vector space, I'm going to take B prime, another linearly independent subset of the vector space, which contains B. So what do I know? Well, the cardinality of B is less or equal than the cardinality of B prime because B is a subset of B prime. But on the other hand, the cardinality of B prime cannot be any more than the cardinality of C because B prime is linearly independent while C is spanning. That's again from our main theorem. And thus B prime must be equal to B because B prime and B, as you can see, have the same cardinality. Indeed, the cardinality of B is a dimension of the space, and so is the cardinality of C. So B is indeed maximal linearly independent, and so it's a basis. Similarly, if B is a spanning set and it has cardinality as a dimension of the space, then you would prove that B is minimal among all the spanning sets, and therefore B must be a basis as well. So this is a very, very common way to prove that something is a basis when you happen to know the dimension of the space you're working with to begin with. And now we are going to in fact move toward indeed showing how to calculate the dimension of various types of spaces based on knowledge of the dimension of other spaces they're constructed from. And to start with, I want to give you a fundamental isomorphism. So here I'm going to prove a general result first. I'm going to say let V and W be two vector spaces where V has at least one basis. So as we discussed, it is slightly unclear under what conditions in general a vector space has a basis, though if V in particular is finite dimensional, then we know it has a basis. And let phi now be linear from V to W. And the following assertions are equivalent. 1, phi is a linear isomorphism, so it's linear and bijective. 2, for all possible bases B of V, the set phi of B is also a basis of W. And 3, there exists a basis of V, whose image in W by phi is also a basis. So let's prove our result. I'm going to assume 1, that is, I'm going to assume that phi is a linear isomorphism from V to W, and I'm going to take B a basis for V. I want to prove that phi of B is a basis as well, so I need to prove first of all that it is linearly independent. So let T1 etc. Tn be scalars, and let V1 etc. Vn be a subset of B, such that T1 phi of V1 plus T2 phi of V2 plus etc. plus Tn phi of Vn equals to 0. As phi is linear, that means that 0 is also equal to phi of T1 V1 plus etc. plus Tn Vn. And since phi is injective, the only vector that's mapped to 0 is 0, so T1 V1 plus etc. plus Tn Vn must be 0. But since B is linearly independent, this means that T1 must be equal to T2 must be equal to etc. must be equal to Tn must be 0. So phi of B is indeed linearly independent as desired. So then I want to prove that phi of B is spanning. So let omega be in W. Then omega must be phi of some V in the vector space domain of phi because phi is surjective as a linear isomorphism. Now, since B is a basis, V is a linear combination of vectors in B. So I'm going to write V as T1 V1 plus etc. plus Tn Vn, with again the T's scalars, and V1 to Vn some subset of B. As B is linear, omega equals phi of V, so it's equal to phi of that linear combination, T1 V1 plus etc. plus Tn Vn, but it's then equal to T1 phi of V1 plus etc. plus Tn phi of Vn. And that's in the linear span of phi of B. By definition, it's a linear combination of vectors in phi of B. So phi of B is spanning and linearly independent, and therefore, by definition, it is a basis for W. So 1 implies 2. Now, of course, 2 implies 3. So let's assume 3. That is, we assume now that there exists a basis B of the vector space V such that phi of B is a basis for the vector space W. So my point is now I want to prove 1. So I want to prove such a phi must be an isomorphism. Well, it's already linear, so all I need to prove is that phi is bijective. And thus, I want to prove that phi is both injective and surjective. Let's start with injective. So since phi is linear, to prove phi is injective, it is sufficient to calculate its kernel and prove its kernel is reduced to the singleton 0. The kernel contains 0, so all I have to prove, in fact, is that if I take a vector in the kernel of phi, that vector must be 0. Now, let V be a vector in the kernel of phi. Since B is a basis for the vector space domain of phi, there exists V1, etc. Vn subset of B and scalars T1 to Tn, such that V is a linear combination T1 V1 plus etc. plus Tn Vn. So when I apply phi to V, I get 0. So when I apply phi to this linear combination, I get 0. But what phi of this linear combination is the linear combination T1 phi of V1 plus etc. plus Tn phi of Vn, since phi is linear. And now I know that phi of V1, etc., phi of Vn is a subset of phi of B, and by assumption number 3, phi of B is a basis of W. Therefore, I can conclude that it is in particular linearly independent, and thus T1 equals, etc., equals Tn equals 0. Because we were able to write a linear combination of vectors in a basis that's equal to 0, all the coefficients must be null. But then let's go back to what V was. What V was T1 V1 plus etc. plus Tn Vn. Since all the T's are 0, it shows that V is 0. And thus I've shown the kernel of phi is reduced to the singleton 0. So phi is certainly injective. Moreover, since phi of B is a basis, W is the linear span of phi of B. But B is a subset of the domain of phi, so the linear span of phi of B is a subset of the linear span of phi of the entire space. In other words, it is a subset of the linear span of the range of phi. But we've learned the range of a linear map is already a subspace. So we conclude that W is in fact a subset of the range of phi, which itself again is a subset of W, of course. So by double inclusion, the range of phi must be all of W, and thus phi is also surjective. So phi is a linear bijection, and we've shown already that this means phi is a linear isomorphism. And so 3 implies 1. So here is a corollary of this observation. Let V and W be two vector spaces, and let's say V is finite dimensional. So in particular, V admits a basis. Then I can apply my theorem, and what does it tell me? It tells me that if V and W are linearly isomorphic, there exists a linear isomorphism between V and W, then the dimension of V and the dimension of W are the same. In particular, I'm saying that W is also finite dimensional. And then there is a sort of converse, which is that if the dimension of V equals the dimension of W, then in particular, of course, W is assumed finite dimensional, then V and W must be linearly isomorphic. So the dimension is a complete invariant for finite dimensional vector spaces up to linear isomorphism. What this sentence means is if you give me two finite dimensional vector spaces and you can calculate the dimensions, you know if they are the same, that is linear isomorphic or not, simply by saying, are the dimensions the same or not? That's what this theorem tells you. The proof is really a direct application of the theorem above. So for instance, assume that V and W are linearly isomorphic, and let phi be a linear isomorphism from V to W. Then pick B some basis of V. V is finite dimensional, it has basis. Then phi of B is a basis of W. That's what implication 1 to 2 of the main theorem above tells us. But then phi is a bijection, so in particular it preserves cardinality. So the cardinality of phi of B is a cardinality of B, which is finite, so W is finite dimensional, and in fact, even better, that means that the dimension of V is the dimension of W. Now assume on the contrary that the dimension of V is known to be the dimension of W. So V has a basis of, say, n elements, V1 to Vn, where n is a dimension of V. And W has a basis, let's see, W1 to Wn, with the same number of elements because they have the same dimension. Now, we can set phi as a unique linear extension of the map which sends V sub j to W sub j for each j between 1 and n. So in other words, phi is a unique linear map such phi of V1 is W1, phi of v2 is w2, etc. I can do that. We know that given that v1, etc. to vn is a basis for my vector space v, I can define such a linear map, and it's in fact unique. But then by construction, it maps a basis to a basis, and therefore, again, using our theorem, it must be a linear isomorphism from v onto w. And my theorem is shown. So this tells you why the dimension is a very useful tool. It is, again, a complete invariant of finite dimensional vector spaces. It characterizes finite dimensional vector spaces up to linear isomorphism completely. On the other hand, see how I made this isomorphism, that is in particular how I proved 2 here in this little theorem. It turns out that I had to choose a basis of v and choose a basis of w. So the linear isomorphism does not come for free. You have to make a choice, and there are many bases in general for an arbitrary vector space. You should not expect, of course, that there is only one. So in general, there are many choices of which linear isomorphism you could talk about, and this is actually an interesting issue. So now that we have established that the dimension is a complete invariant for finite dimensional vector spaces, we wish to be able to compute this dimension for many of the construction of vector spaces we have encountered. This will be the topic of our next lecture, which will devise method to compute the dimension of products and quotient vector spaces, and conclude with the very important theorem called the rank theorem.